Hello, calculus. So far, up until this point, and right now we are on page 7, we have looked at limit problems dealing with direct substitution. Again, the entire last section, reviewing all these types of problems, knowing how to use the limit properties, proves and shows that direct substitution works, but not all the time. And so we're going to look at some of those exceptions, hence this little sad meme face right here. Because it's probably what you're feeling, right? You're just saying, like, man, we just got used to direct substitution, seeing that it works, which was magical, and now I'm throwing these cases at you where direct substitution is not going to work. So you're probably asking yourself, well, how do we know if direct substitution doesn't work? And it's going to be when you get problems where you get either 0 over 0. That is a math error. I call it, it's one of the 7 deadly sins of math. We'll get to a few more later on in the school year. Or you get infinity over infinity. Those are going to be the 2 errors that we're going to be looking at here. So reviewing example 6 before I just crush your souls, we are going to show that we can use direct substitution here. So I'm going to plug -1 in and just see what we get. So if I take the limit, and again, I'm using my limit properties here, so I'm going to separate my 2 problems. We get the limit as x approaches -1 of the function x plus 1. All over the limit as x approaches -1 for my denominator function, which is going to be x squared minus 1. When I do this, when I plug -1 into my numerator, I get -1 plus 1 over, plug -1 into my denominator, and I'm going to get -1 squared minus 1. And you can see that big error here, right? What is my limit? Well, we don't know. And it's because direct substitution doesn't 100% work all the time. So some different algebraic ways that we can find a limit. So again, the reason why step 1 has all these stars is generally you want to always try direct substitution. Because if direct substitution works, you get your limit, you're done, call it a day. So easy peasy. So we are going to be looking at these different methods here. So really we're going to be focusing on 2 through 6. And seeing what those problems look like and how you can start identifying problems where chances are direct substitution is not going to work. So type 1, right, is direct substitution, showing that it works. So before we get started, there's a very special math term where I call it a very bad time. We want to avoid these bad times so that we can actually get our answer. And that term is called an indeterminate form. So indeterminate form. So the 0 over 0 and infinity over infinity forms, those are called indeterminate forms. So whenever you get an indeterminate form, that just tells you direct substitution does not work. So then you have to use a different method in order to find the limit. So type 1 here is just proving and showing that direct substitution works. So again, just like example 1, how I'm going to use this is I'm going to use my limit properties to separate my 2 numerator and denominator limits. So we're just going to work through that pretty quickly. And then we plug 5 in. So here we will get 25 minus 30 plus 8 all over 5 minus 4. So I can see my denominator is just going to be 1, so I can just really focus on my numerator. So 25 minus 30 gives me -5. -5 plus 8 gives me 3. So again, when you can use direct substitution, it's great because you just plug and chug and call it a day. So our first error here, and the first type of method we're going to introduce, is we are going to show how you can use your factoring skills in order to actually solve this limit. So first, again, we always try direct substitution. So Example 1 up here, or really example 6, this is actually poor notation. So I'm going to draw a big X through it because this is not how you justify an indeterminate form in calculus. And I'm going to show you the proper way on how to do that down here. So maybe you can quickly see, right, if I plug 4 into my denominator, that's going to give me 0, which is a good signal that something bad is about to happen. And then when we plug 4 into my numerator, hopefully you can do that math pretty quickly, and you can see that your numerator will also become 0, and so I get 0 over 0. Now, how do we justify that, or how do we write this out using calculus and proper notation? So what you need to show is you need to show that your numerator limit and your denominator limit equal 0 separately, because we are going to see that you will still end up with a limit. So we can't say that this limit here equals 0 over 0 because there is an actual limit here, especially if I give you a graph. So we can't say 0 over 0 equals, say, 2, because that is not true. So just be careful on what you say is hard, like the hard equal sign. So what we do here is we take the numerator limit, as x approaches 4, of my numerator. And if you did that mental math in your head, that's totally fine. You can just say this equals 0. Then you can do the same thing with your denominator limit. So as x approaches 4 of x minus 4 equals 0. And so once you establish that you have a numerator limit of 0 and a denominator limit of 0, then all you can do is put these 3 triangle dots. This stands for therefore, and you can just say therefore it's indeterminate. Which identifies that you are using a different method here, okay? So all of this work you have to show. So I'm going to highlight this. This is very key. You have to prove and show that your function has an indeterminate type of limit before you use one of these methods. So that is very key. And then here, what we're going to do is we're going to try factoring and see what we get. So, okay, we're going to go back to the drawing board. We're going to start with my beginning limit. So I'm just going to copy it down again. Oops, there should be an X there. And let's go ahead and try factoring. So what we're going to do here is we're going to leave our denominator alone because we can't factor that. And then we're going to figure out, okay, well, what multiplies to 8 and adds to negative 6? So we get 4 and 2. So we get x minus 4 and x minus 2. And then hopefully you can see that the x minus 4 group cancels. Now, jumping to pre-cal again, kind of brainstorming on what we're identifying here, if I have a group from the numerator cancel out with something from my denominator, again, this represents my whole on this polynomial, or on this rational function, right? So try and remember that when you are factoring, right? When you're noticing and canceling out these groups here, you are stating that you are identifying the whole, which is why when you plugged 4 into this original problem, we got that indeterminate form because it was noticing a whole. If we keep going on, so once we identify that whole, then we just say equals the limit as x approaches 4 by my function x minus 2. And then from here, you can plug 4 in for x and see that your limit is 2. So there is a typo down here. There's lots of typos, actually. This should say indeterminate, but how I spelled it earlier. So this should say indeterminate. Okay, so just a couple typos there. So just bear with me. Okay, so that method isn't too bad. We can amp it up just a little bit, right? And we can look at type 3, again, which is called rationalizing. Again, before you use the type 3 method that I'm about to show you, you first have to establish that you have an indeterminate form. Again, to do that, you take the limit of your numerator and you establish that that does in fact equal 0. So you can see here, if I plug 13 in, I get 13 minus 4, which is 9. Square root of 9 is 3. 3 minus 3 is in fact 0. And then we do the same thing for our denominator. So the limit as x approaches 13 of x minus 13. We can say that's also 0. So therefore, this is establishing that we have an indeterminate form. So we can say, therefore, indeterminate. Again, once we establish it's indeterminate, then we can use this method. And here we have a square root function. And so we're going to use the method called rationalizing. So that term might sound familiar to you guys from pre-cal. We did rationalize a lot, especially with trig functions. Oh, why can I draw a straight line? So we are trying to rewrite our problem with the square root. So I will show you how to do that in just a second. So again, always rewrite your problem. And then here we're going to rationalize. And in this problem, we're actually rationalizing our numerator because that is the spot that has the square root. So the way you rationalize is you keep your square root the same. So this still is x minus 4. You keep your constant the same, which is 3, but then you change the sign in between the two. And I'll explain why after we multiply this out so that you can see why we choose these two values. Now we can do this mathematically because if you see what's in red, it's the same thing divided by itself, which is in fact 1. So we're multiplying our original problem, our original function here, by 1. It's just a different ratio of 1, right? So we're changing how our problem looks, but not how it behaves. Okay, so then just keep in mind that my numerator is a group and the parts in red are a group. And so we will have to FOIL here. So don't forget your limit notation. So we need the limit as x approaches 13 of, and we only need to distribute our numerator. We can leave the denominator alone. We only need to FOIL the part that we are rationalizing. And in this case, it's where the original square root exists. So again, let's go ahead and FOIL. So if I take the square root of x minus 4 times itself, this just becomes the group x minus 4. If I do my outer and inner terms, those two terms are opposite signs. So I get square root of x minus 4 times 3, and then square root of x minus 4 times negative 3. So I can quickly see that those two terms with opposite signs are going to add up to 0. And then my last term is my negative 3 times 3, and I get minus 9. And then we're going to leave our denominator alone. So we're going to leave this as the group x minus 13 times the square root of x minus 4 plus 3. Hopefully you start seeing something. All right, so in my numerator, I can combine my terms and I get x minus 13. Leave and copy down my denominator as is. And then hopefully you notice this x minus 13 group cancels. So just to summarize all of this stuff, because there was a lot, going back to the rationalizing step, which is where we did our work in red over here, where we are multiplying by the numerator term, but with an opposite sign here. So the reason why we choose this is so that our square root completely disappears on the other side. This takes the same idea as the factoring of perfect squares, right, where we don't get that bx term. It's the same idea. We want to get rid of the square root, and we don't want any term with a square root to remain. So we just do the opposite sign so that my square root cancels. And again, we leave our denominator alone because that's not the piece we're rationalizing, and it's because that original denominator should always cancel with the numerator. Okay, so that's a good checkpoint right here, is you should see a cancellation happen somewhere. If you don't, that just probably means that you did your algebra wrong. I get questions about calculus all the time. Is calculus hard? And I say no. I think calculus concepts are quite simple, but what trips up students more times than not is going to be the algebra. So just work problem slow, show your work, and you should be okay. All right. finishing up this problem, so I'm left with 1 over the square root of x minus 4 minus 3 term. And then now we're just going to try direct substitution. So I get 1 over the square root of 13 minus 4. Oop, that should say plus 3. And then we just simplify this problem. So 13 minus 4 is 9. Square root of 9 becomes 3. And then I get 3 plus 3, which is 6. So my limit, my final limit is 1/6. So what I like to do at the very end is, okay, cool, I got my answer, but your work and your answer kind of blend in. So just always make sure and reference the original problem and make sure that you actually answered the question. So what I like to do is I like to go back to the original, copy down the original problem, because again, that is what I was trying to solve for. And I conclude what this limit is. So I say, therefore, this limit is also 1/6. So I like to write both. I think I did not do that in the previous problem, but hopefully you get the general idea. So I'm going to add that here real quick. So I'm going to say, therefore, my original problem, x squared, let's see, minus 6x plus 8, all over x minus 4, also equals 2. A little ahead of myself there. Okay, so we will be looking at type 4, 5, and 6 starting in class next time I see you. So if you have questions about type 2 and type 3, so again, factoring and rationalizing, please come to class with those questions and I will happily answer those. All right, guys, I will see you soon.